Да, всем здрасте.
So, hello everyone, and our next presentation is brought to you by Oleg Bartunov, that you all know, and he will tell you about some very strange and magic things about full text search. So I will keep an eye open on the watch and tell you if you run out of time. Hello, and I'm very happy to be in this magnificent room. I think that we can only be jealous about those who study here. I will tell you something about full-text search. I'm not going to cover all the things. So the name of the topic is just to be more attractive. But I'm not going to tell you about everything about the full-text search because it will take up to 5 hours. So here I will tell you something that will help you to understand what is full text, why can you use it, why should you use it. And at the end of my presentation I will give you some links to my full report, which takes 5 hours. So if you don't know, in my presentations I'm using this image. It is an image that was drew by monks. It's from Tibet. I just couldn't help buying this because a lot of very interesting things are in the picture. You can see our elephant that turns from black to white. I can compare it, and I can find the stage where I am, where our Postgres is, and I share this image with you. It's very good. I like it. If you don't know, I am a developer and a Postgres contributor since 1995. I've been working in Sternberg University, which is not far from this building, and I am a Postgres professional CEO, which is the organizer that I have founded together with my friends and colleagues 5 years ago. And here you can see our elephant, and you can see the number of projects that I have been working on. So what am I going to tell you about? I will tell you what text search is in PostgreSQL. Then I will answer the question why we need full text search if we have Elasticsearch or Sphinx or something else. This is a very popular question, and then I will go through the main topics: basics of FTS, mastering FTS, how to accelerate FTS, and also I will tell you something about future of FTS. So what is full text search or FTS? FTS is when you have some documents and you want to match these documents a query. Why I say match? Because you can have your own understanding of match, like all words, part of words, accurate match, not accurate match. So opinions can be different. That's why we don't say contain, we say match, that correspond a query. And these documents are optional. People want to get them in a certain order, and this order can be defined not only like whether it looks similar to your query or it's a fresh document. It's absolutely up to you how you define it. So a typical search is to find documents with all words from the query. It's what we do every time in Google or in Yandex. We put some words and we are looking for documents that contain these words. Then we can argue whether Yandex is better than Google or not, but all people have their own understanding over the document, which document is more relevant to them. For example, previously people could judge. Now when we work in commerce world, these range functions have a lot of different information which doesn't correspond to the full text search. For example, you go to a shop, you see something, you find something, and then your full text search takes into account your interests and it starts recommending you documents that don't only match a query, but also they match your entire life. And we do the same sometime. sometimes. But what IT people want from Google is that a document contains all words from the query and was sorted by relevance. In fact, what is a document? It's a very virtual notion because document used to be a text, an article, something tangible. With the digitalization era, we understand that document is a web page and we refer to this web page. But we understand that all these pages are being born out of a database. And a document in a database is something virtual. This document can not even exist. Maybe this document is just a result of a big, massive join of 5 joins. It is not materializable at all. So that's why in databases we cannot say that document is something that is stored on a drive. It's like a file and we can find it. No, it's just a result of a query. For example, we have messages table, we have lists table, and a document is just a result of a simple join operation. So also don't forget about coalesce function. If you start using with databases, they think that if we concatenate 2 text documents and one of them is just null, this null equals to emptiness. But in databases it's not like this, because you will get a null. That's why don't forget about coalesce, so your result corresponds to our expectations. And what is a query? Query is a kind of arbitrary text. It can be a document. It contains some words. A query that was written on a certain language. So here you can see an example of what we can type in Google, like PostgreSQL, open source, multiply database, which means complete match minus die. It means that die shouldn't be contained, but it should contain most. So it's a kind of a query language. These languages are multiple. We used to use logical queries like null, node, contains, but people are using these kind of things like phrase, search, and so on. So you have some understanding of what is FTS and what I'm talking about. And now, the most tricky question: why we need FTS if we have other external engines, and these engines are quite rapid. You can use Elasticsearch, it is fast, it is scalable, it has Sphinx, and so on. But as I said, there are a lot of situations when you need embedded engine. For example, you cannot index all documents because they are totally virtual, they do not exist. If you have a lot of tables, your system is big, documents can be generated just by queries results. And these documents are virtual, they are not available for external engines. There is a notion hidden web. What Google indexes, they say that by dozens of times they cannot index everything. They can index only what we give them away, and we don't give everything out of the database. That's why you can't index all documents. Not everything is available for search engines. So this is the reason why databases can virtually generate a large arrays of documents. These external engines don't have access to attributes. We understand we have a table, we have columns, we have generated a document out of a query, but also we have additional attributes like filtering, sorting. External engines don't have access to these attributes. So they can only work with what you give away out of your database and what can be indexed. External engines should be maintained, and this is a headache for DBAs, especially when it comes to Elasticsearch, because They can crash, you have to maintain them. I saw a system with Sphinx, and there is another daemon on top of them that is monitoring them, and another daemon of that daemon. So just another point of failure, additional point of failure that you don't need. Some systems must be certified, which is another problem. Elasticsearch is not certified, and it cannot be certified because Elasticsearch owners would say we don't need this. But in our reality, for some systems, especially those that process personal data, you have to have an engine that is compliant with their requirements. It doesn't matter whether this requirement is good or bad, but they exist and you have to be compliant with them. And PostgreSQL has an embedded search engine, and Postgres, our version of Postgres is certified. Moreover, sometimes in big systems you want to have an immediate snapshots. In order to have something out of the external search engine, you have to feed it. In databases, everything is embedded. Once you make an insert, everything is available right away. And we are used to it. And sometimes when you just submit a document to a video or someone else, you will not find it. But they are so sly in a video. They say we've got 15 seconds to check it, but actually they're just indexing it because they don't know how to deal with it, how to handle it. Maybe it's just a funny joke, but really for DBAs, it's a normal thing, it's a typical thing. Every time you make an insert, you're looking for it. External search engines do not support it. They're trying to cut down this lag. They have incremental indexes, but there are situations when you need this result right here, right now. What about consistency? Everyone knows that once you find something, you click it and you don't see a document. You get an error 404 or something like this because database content and what was given away. So these things can differ. So there is no notion like a transaction approach towards external things because database is being maintained in a consistent way. That's why we love it. But what we give away, documents could change, they could be updated, or they could disappear, and this is a headache. For a typical internet service, that's something normal. It doesn't exist, no problem. But for serious systems that when it comes to, for example, something very big and expensive, what if you go to state procurement's website and you don't find a document? I think we've got some people from this state procurement portal. So 5 or 6 years ago, they were using MongoDB. There was some problem. In Postgres, maybe it is slower than MongoDB. But in terms of data consistency, everything is better than in MongoDB. Also, there is another case that is not on the slide. Sometimes you want to have different results for different people. In Postgres, there are roles. There are super roles, like I want to have access to all documents, to all results, and there are ordinary people, like we give you something and that's it. External search engines cannot do it because external search engines cannot get we cannot pass such privileges to external search engines, especially when you have mandate system. In Postgres, you can just filter results, and external search engines cannot do this. So full text search is very important, is very helpful in Postgres, and we did it back in 1999, if I'm not mistaken. We started working on this project, and we have been maintaining this project. If you do it differently, your system will look like this. So it will work somehow. It will work for sure, but because of these crutches and external engines, it will suffer, and you will suffer too. Okay, what about our tasks and what about FTS requirements? So, first, full integration with database engine. I mean, complete integration. Because you can work with FTS by using objects and operators like with other things in PostgreSQL. Materialized views, simple views, joins, selects. Everything is available, everything is usual. Transactionless, specific transactions, concurrent access, recovery, online indexes. And also, we wanted to make FTS configurable. We mentioned that the notion of search is different, and we have to give this configurability capability to users. We should provide users with different passes, dictionaries, and so on. And of course, we need to make it work faster. There was a great deal of efforts to make FTS faster, and we always match the performance of external search engine. So traditional text search operators are like this one, very known operators like text, optext, text with asterisks, like, I like. You can use them and everything will work. You type something, you find something. There is only one problem, is that there is no linguistic support in such queries because these operators do not understand what is word, what is index. They don't know how to normalize these words, whether all words should be indexed, and there is no natural ranking. There is no notion of ranking because all documents match a query. And since no indexes are supported, this is quite a slow process. Starting from version 9.3, we started to support this operator till the asterisk. It is a 3 grams search, and in red you see it's quite a sophisticated query, and it allows you to look for something more sophisticated, but it looks ugly. So in 2000 we made OpenFTS, and it is to be noted that we made this FTS vector and we did it with Perl. We did it externally. So OpenFTS is a Perl-based scripts, and it created a document and stored it in Postgres. In Rambler, we made the first gist index, then we made ranking, then we've made a tsearch 2. In 2006, Gene came out, and I think most of you know what Gene is all about. And in 2006, thanks to Enterprise DB, we committed this into core, and then we just promoted this, developed this, and RAM is another solution of ours. It's a very interesting solution, and I will tell you about this later on. Different people took part in this project, including me, Theodore, Oleg, and many others. But now I want to tell you about basics of FTS. In fact, all FTS is covered by everything you see on this slide. The rest is just to make your life easier. In reality, you just have to have 2 types in one operator. You see, data type is TS vector. It's just a data type for document optimized. What means optimized? It means that all lexems are sorted. There is information on position, and also there is some structural information, whether the word is in the title or in body. So it's up to you. It's up to you to define the structure of the document. So that's it. It's a document that gets this kind of type. And the second type is a TS query. And you put your query into this operator. It's just a row with some syntax. And there are two adds, which is an operator. By typing this, you can perform this matching. You see what we will get: cat and rat. It will return true, and all FTS is just in front of you. So you can just write TS vector, you put your query, and then you apply an operator. And then by using your favorite language, Python or Java, you can create this TS vector. You can do it, you can write a query, and then apply this operator. And a lot of people write their search engines without using primitives. And I know, and I was inspired by a chemical formula search, so people just, what is chemical formula? They use special characters in order to put this formula. If you know your topic, you can write your own parser just to split your document into smaller pieces, and then you're just looking for this specific chemical formula.
They don't even need our full text search. They only need these types of data because it's all implemented there. And there is also formula search. We've been making this because majority of the research articles, they are written with a lot of the tag characters, and each picture there, each image there, it also generated in the written form. So you can just look for it like E equals MC squared, and you can really find it easily with this engine. So this slide describes everything. So just remember that you don't have to, you can write anything you want using any language you want, with any flexibility you need. The devil is in detail is as usual. For example, you want words cat and cats to the plural form and singular form to be treated in the same way. It's up to you. You can come up with your own dictionary. What we did in Perl. In Perl, we had our own dictionaries that processed the text and then made something more common out of it. So you can change the queries. I remember when Kursk submarine sunk. Probably a lot of you weren't even born back then, and the older of you, they remember that all the online agencies, online news agencies, they didn't have any pictures, or they were glitching because workload was such high that people couldn't find anything. I worked in Rambler. Our Postgres didn't crash back then, but our headache was that people were getting the page about the city of Kursk. Obviously, city of Kursk was more relevant when they were typing in Kursk. But we all understood that we need to give the information about the submarine to the people. And back then, we just rewrote a query. When we saw Kursk, we were automatically adding to it submarine Kursk and boat Kursk, and then it worked fine. And there are a lot of different possibilities. They only limited your imagination. And then we came to the concept of full text configuration for the simpler people. They could use the search without going into these TS vectors and other details. So we gave a certain interface for all these types. So one of them is a parser. Parser by default does exist. When you use full text search, you don't even know that it runs as well. So parser is the small program that breaks the text into tokens. Tokens then defines automatically the type of its token, whether it's an email or a number or anything else. So then you get this pair. And this token then turned into a lexeme via dictionaries, and for each type of token, its own dictionary is used. Not even one dictionary, but multiple dictionaries. For example, if you got the full number, then you might want to cut it a little, because indexing the space of the full number, it is impossible because it's infinite. So you just say then 6 and like you are making prefix search, everything that is bigger than 6, more than 6 digits, then you just cut it there, just kind of a hammer, and then you put it into a database, and then the search engine would work. And if you got an email, then you could group it by domains or by something else, I don't know. So these dictionaries, are defined by you for each type of a lexeme. The scalability, extendability is that this parser, you can replace dictionaries without referring to me, pointing at me. For example, if the inbuilt parser is not working well, you can change it, you can fix it, you can give it a different name, and then you can work with the new one in your configuration. The same goes for dictionaries. And all this configuration is connecting parser and dictionaries. In PSQL, you can use these comments \d, capital F, and then P, D, or plus to get the information about the full text search and full text configuration. And in addition to that, we also added SQL interface so that you could, with ordinary, normal, common English language, to configure it all. To turn document into TS vector using just ordinary functions, we have this function toTS vector. The first argument is the configuration, the name of the configuration. English or Russian, that's what is by default. I think they support 23 languages automatically. They are available to any Postgres administrator in the version 12. So configuration, and then you don't even have to specify it, because then it's taken by default, like in your database, current database, then it's taken from there, but you should rather specify it. And another argument is text, any text, a column or text itself, or it could be JSON or JSONB. So now JSON starts support that you can just index it like that, the full text ones. Configuration, as I said, the full text configuration. If it's not specified, then they take a variable by the default text search config. And just as an example, when you get this query, you make this query, and then you can see that the word false, and you can see 10 after it. The 10 is the position of the word in the document. And then long is 5, and story is turned into, you can see it now, into an I letter by the English rules. So a stammer was used, that you all know, and Y was turned into I so that you could be able to find it. And that's okay, because when you search for it in this query, the same very dictionary would be referred to, and it would do the same, and you will find what you were looking for. That's what consistency is. So example of such dictionary is simple. It has a factor in here. Oh, simple, yes, I made a mistake here. Simple turned this dictionary, so nothing has changed. Yes, it's not a toTS vector. Oh, no, it's a simple configuration. That's right, everything is right here. So by default, it refers to English, Russian, the languages that you use. There is also a simple configuration to fine-tune it when it refers to one dictionary, and then puts everything into lowercase letters, and you see how it all works. JSONB toTS vector, that's something that we have got just recently, and you understand why results are different for JSONB, for JSON and JSONB, because JSONB, it doesn't keep the order, the initial order. So obviously the results are going to vary slightly. So you can see examples in here, so you see how it could be easily done, and at the same time you can still have the positional information, and it's used for phrasal search. Phrasal search is something that is a very interesting thing when you're looking for documents that contain not just certain words in different parts of the document, but when you specify that these two words should go together in this particular order, and then you understand that you found what you've been looking for, because you could find a document where one word is in the beginning of the document, the other word is at the end of the document, so it's not really relevant information, not really relevant search results. So we have this function to edit TS vector, for example. You can mark, you can tag different parts of the document so that in the future you can use it to arrange it. So you see here the function setWay, and you are basically saying that this array of text, each word must be marked with this mark char, and you can use four marks A, B, C, and D. So why do you have those? So that in the future, when it is arranged, you could specify the weight for each mark. For example, you are requesting, I'm searching for certain phrase, but at the same time, the words from the title are 10 times more important than the words from the actual document. Or you can do it the other way around. It is up to you. So these are just marks. And what does this mark mean? What is its meaning? You can, of course, specify it later. And there is a function tsDelete. When you just have a TS vector, you can delete something from it. You want to destroy something in it. So here we deleted 20 PostgreSQL for whatever reason. And very useful function. Unnest. Unnest is a thing that nests an array. So here we are nesting TS vector, and we show it as lexem, position, and weights. It could be useful sometime, for example, to make a join with something and to create something cool out of it. There is a TS vector 2 array. You can present it, display it as an array for some manipulations. There is a TS filter. For example, you've got a TS vector that you've made and you want to cut everything out from them related to titles, for example. You just filter it all out with specifying a mark or marks. And this text, this array, you can put marks in there, A, B, C, and so on and so forth. And you can see the results here. That's where we filtered out everything related to the mark C, and we got a result or a second example to filter out everything relating to C and A marks. For the better understanding of how such queries work, I created this picture so you can see there is a document on the top of the page, and then it feeds everything to parser. Parser, it's the document, and then it gives you token and token type, this pair. Then it goes to an array of dictionaries. And then for each dictionary, we are trying to see, does dictionary recognize the word or not? For the simplest dictionary, that's how this logic works. If I know this word, I will put into TS vector, and then I'm exiting the process is over. If I don't know the word, I will pass it on to the next dictionary. Maybe some of the next dictionaries will recognize the word. And so it goes on, so that's how it's processed. And by default, we have 23 types of tokens. So you can see here there is a query, token type, and default is parser. So default and parser, they recognize 23 tokens. Actually, people are asking why so many? We only need words, but actually, people, life is bigger than that. Sometimes we want more. People start indexing XML tags, for example. You have this. Dictionary is a program which accepts token on input and returns an array of lexems. And there is a function tsLexsize that shows. So just an example here in front of you. Elephant. Now and so on and so forth. And dictionaries, so you can use API to create a custom dictionary. You can write a dictionary that will stem along numbers, would convert colors. It was a real example from real life because we're writing white and black in English and Russian, We can write different kinds of colors. But when you're looking for colors, you would like to write something, one type of colors. And using dictionary, you can turn all these colors into something in one type of colors and then search for it. Or you can use and turn URLs into a certain form. For example, there is a dictionary for phone numbers, complete numbers. For example, historians wanted me to write that because historians got sick of writing, of Googling 19th century with the Roman figures, with Arabic figures, numbers. But if you create a dictionary that would understand both, then you can just easily create a convenient interface for them. Or the example for colors in here, FFS is the same as light here, and your user is not going to type in specifically light or something else and the 6 digits number. They can just put down white in here. Just an example of astronomical dictionary to look for astronomical objects, because each catalog, and there are hundreds of them, names objects with different words. For example, you know that Andromeda is actually M31, and you're looking for M31 and you want to find Andromeda. But using this PCRL library, I guess people here are familiar with that, we wrote this kind of a dictionary. So built-in dictionaries, we have a simple dictionary, synonym dictionary. For example, Postgres and PGSQL are synonyms, for example, there. Tethers, when you take the whole phrase into something different, something else. Stammer is the dictionary that understands, recognizes any word. It just uses certain rules to cut this word, to stamp this word. There are laws, rules for each language. The same goes. It's one of the most popular dictionaries, actually. For example, Portuguese stammer, you see how this works. We give viva, vivo, viver, and we see how different words are turned into the same query. So it allows you to look for different forms of the word. So it's all a part of the kernel. iSpell is widely known dictionary that is used in OpenOffice and LibreOffice. It's available for a lot of languages. You can use it for the Russian language. We are using it for morphology. For example, you're saying Putin, and then it will return Putina to you. It supports iSpell, MySpell, and other spell checkers. They are also filtered dictionary, unlike the simple dictionary that would recognize a word and that would write it as vector. A filtered dictionary allows you to recognize the word and pass it on to the next dictionary. So for that dictionary to do all the work. For example, it will clear the word out of all the accents, all the umlauts, and then we'll pass it on to the next dictionary that would do its job. Obviously, the stack of dictionaries should go from the bigger one, from the narrower ones to the bigger ones first. Astronomical dictionary, then Russian language dictionary, then a stammer that would recognize everything. Here is an example of unaccent. I'm being told that we are running out of time, so I'm just running through it. So that's how the query is processed. You can see that it's a little more complicated than the dictionary. It uses the same dictionaries, but actually it is built so there is the tree of queries. You can see it here. If like supernova stars is coming as a query, then that's what you get. So the tree is created. The root there is an AND operator, and each word is broken by the dictionary, processed by the dictionaries according to the rule. Supernova is turned into two words, actually, supernova, and then contraction, SM. So stars has become a star. And then the query tree is built, and you can see that it looks quite complicated. So the result of this search, and then it's a supernova, and that's how it is processed by the dictionaries. Query processing. So we have this function, 2ts query, the same as that 2s factor works. There's a plain 2s query because A lot of people, they don't understand ANDs because in 2 query, the language that is written on certain logic language, supernovas, must be written and stars. That's how it rotates. And people just want to put their supernova stars, so they want to type it in and then they get error in return. So to avoid this, we need to use plain 2 query that would understand the common people language. We also have a phrase 2 query. You can put here this function, and then everything that was written there would be apprehended as a phrase, would be recognized as a phrase. And there is a web search 2 query for those who are more familiar with the Google search language. So you're writing it like that, and then you're getting the result just like at Google. There are a lot of additional functions, and I can go on talking about this, but these are just tools. As you remember the slide that I showed you in the beginning, that was the main slide. And all this rest, it just evolved into this, and people just wanted to use it for the more convenience. So what I wanted to say as a summary, so it's a flexible search engine, and it's a it's very much in demand, but basically it's just a set of the building stones that you can use to build your own search engine, and you can use all the power of SQL. You can combine full text search with the spatial search, with the temporal search. It's just your imagination is the only limit. As for indexes, I like to say that that's not really a silver bullet, but it really makes your life easier. We have GIST indexes. It's almost not used at all because it's not really scalable. The inverted E index, which is used in a lot of places, but it's the same instance. And the last one is RUM. RUM is something that allows you to speed up some queries, like looking for phrases, searching for phrases, ranging. So it is really quick, and it's production capabilities almost as good as the external search engines. So there is a description of what it is, and we also have a number of really useful extensions. These are dictionaries that are stored in the shared memory. I have a slide and where I have links for these extensions. If you're too lazy, you can just download an extension and you right away will have all these dictionaries and all the necessary configurations, the shared memory. Just as an example of how a normal search is working, that's our search in the documentation. You know our Russian documentation on the website, so that's where we use the full text search. That's where we use our own parser, customized parser. Here's an example of why we decided to make this parser. So we use face-edit search there, and people ask me how to do a face-edit search. Yes, I am almost done. And so it is all here in this example to see how it looks like. And in version 13, there are two new nice things. Now you can write a query like this, something from, and then to test query. Q, and you can use this Q everywhere. So, and then it will go. Before version 13, it was a problem. We had to, instead of Q, we had to this query everywhere and so on and so forth. And now you can use an alias and use this one. It works perfectly. It's the patch that was made by our company that we managed to use after almost a year. And for Gin, for such queries, the full index scan is not performed anymore because not star, it was a very difficult query because Gin had to scan the whole index to find it, and now Gin has become wiser and is not going to use the full index scan in a situation like this. And you can see all these links in here, so I just made it for you. You can find a lot of additional information. So that's it. Thank you for your attention. Thank you, Oleg. If there are any questions, thank you, Oleg. If there are any questions, does anyone have questions? Yes, I will be here the whole day, the entire day. If someone is really eager to ask me about something at 8 o'clock, I will leave, and people will be living with me, and you can ask me any questions on the run. Oleg, thank you for your talk. So I've got my question about my pain that I had since a long time ago. Why default parser is behaving in a weird way when it doesn't see slash as the separation between words? Because it sees it as a file path or something, because parser, to write a parser that would be on 100%, well, parser is all about heuristics, so it's really hard to differentiate it from URL and the file path, so it's hard for it. So can we, without changing the parser, to regulate this behavior? It is really easy before you are give it to TS vector. Yes, we can with the replacement. Yes, that's what people do. Thank you. Well, I think this is it. Thank you, Oleg, for your report and for your contribution to the development of Postgres, full text search, JSON, and a lot of other things. My question is that I was part of one project where the full text search was implemented with Oracle text, and we needed to look for personalities in the text. For example, Ivanov Ivan Sergeyevich, Ivanov Ivan, Ivanov Ivan Sergeyevich, and the architecture of the text itself was built in the way that the more words we add, they should go next to each other. Then it was just after a couple of million documents, then it didn't work anymore. So Postgres had the same problem. For example, when 3-4 words must be next to each other. No, we don't face these problems, because in a query you just specify that that's a phrase. Then it would work faster, especially RUM is working good with it. So, okay, thank you.